Welcome back, Math 1920, Calculus 2. We're going through Chapter 5, Section 3, Inverse Functions in your book. All right, so let's take a look at an inverse function. First of all, understanding the nomenclature. So now when we see f to the negative 1, it really means f inverse, or the inverse function of f. Okay, so let's take a look at the first one. The domain of one function, or the domain of the original function, is the range of the inverse function, and the range of the original function is the domain of the inverse function. So if we notice, all right, we have a set of points for the original function here, 1, 4, 2, 5, 3, 6, 4, 7. If we look at the inverse function, we swap the x and the y. So the inverse function down below becomes 4, 1, 5, 2, 6, 3, 7, 4. Okay, so like I said before, the domain of the original function is the range of the inverse function, and the range of the original function becomes the domain of the inverse function. Okay, that's really what we mean here, and that's really what this definition of an inverse function is, all right, when we're pulling it out of the book. So just for now, remember, if we see f to the minus 1, we're going to say f inverse when we do this. All right, so when we're taking a look at it, if g is the inverse function of f, then f is the inverse function of g. So they will be inverses of each other. The original and the inverse will be inverses of one another. And like I said before, the domain of f inverse is equal to the range of f. And when we talk about f, the original function, okay, and the range of f inverse is equal to the domain of f. All right, so the range of one is the domain of the other, and vice versa. Okay, a function does not need to have an inverse function, but if it does, the inverse function is unique. Okay, so when we talk about f inverse, we're undoing what was done by f. Okay, so some simple properties here. If we have f of x equals x plus c, we can calculate that f inverse of x equals x minus c. All right, so subtraction is undoing the division. Okay, and if we look at f of x equals c times x, okay, f inverse of x is x divided by c. So we're using division to undo multiplication when we do this. All right, so one way we have to verify inverse functions, all right, and show that they're inverses of one another, okay, is being able to put them into each other. So we're going to treat these as composite functions, or use composites to do this. So we need to find f of g of x, and we need to find g of f of x. If they both equal x, then they are inverses of one another, okay, as we go through this. So that's the simplicity part of it. Find f of g of x, see what it equals. Find g of f of x, see what it equals. If they both equal x, when you simplify them all down, okay, then they are inverses of one another. So we're going to take the composite function first. We're going to find f of g of x. So we're going to take that function g of x, which is the cube root of x plus 1 over 2, and put it in for the x in the f of x function. All right, so we're replacing that, so it becomes 2 times g of x cubed minus 1. Okay, the cube and cube root obviously cancel with each other. Okay, the 2's will cancel each other, right? I have a 2 in the numerator, 2 in the denominator, and we've got multiplication going on. The 2's will cancel each other, okay? And that leaves me with x plus 1, x minus 1. All right, the 1's are going to cancel each other. So I can conclude that f of g of x indeed equals x. Okay, now I got to do the other one. I have to find g of f of x. Okay, so we're going to take f of x and substitute it in for the x in the g function. Okay, you can see that as I've done this, so we're going to substitute 2x cubed minus 1 in for x in the g of x function. Okay, then we can see that the 1's will cancel, so we'll be left with the cube root of 2x cubed over 2. The 2's cancel, all right, so we have the cube root of x cubed, and the cube root and the cube cancel, and indeed x. So we've concluded that f of g of x equals x and g of f of x is equal to x. So now we can conclude that these functions are inverses of one another. okay? And if you were to graph both of them, they reflect over the line y equals x, okay? And you can look at their domain and range of each one, and we can look at specific points, okay? The xy coordinate on f of x is equal to the xy coordinate swapped on the g of x, okay? So when we talk about this, we talk about the reflection property across the line y equals x. So that leaves us with theorem 5.6. Okay, so that's the reflective property. The graph of f contains the point AB if and only if the graph of f inverse contains the point BA. So that's the reflective property, and everything reflects across the line y equals x. Okay, so not every function has an inverse. Okay, but we can use a horizontal line test for an inverse function. If the original function passes the horizontal line test, then it has an inverse, okay, because it has to be 1-to-1. 1-to-1, meaning that every x value, there is only one possible y value ever. All the y values are unique, okay? Not every x can produce, a separate value. Every y value has to be unique when compared to every x value. That's the horizontal line test. So if you draw a horizontal line test anywhere across that function and it touches that function more than once, it does not have an inverse. It doesn't pass the horizontal line test. Okay? So a function has an inverse function if and only if it's 1-to-1. So that's how you test if it's 1-to-1. If it passes the horizontal line test, which means all y values must be unique, okay? And then the second part, if f is strictly monotonic on its entire domain, then it's 1-to-1 and therefore has an inverse. Monotonic means on its domain, it's strictly always increasing or always decreasing. Okay, so that's what monotonic means. So if we take a look at this function here, if we take a look at the graph of x cubed plus x minus 1, it looks like that it's increasing over its entire domain. So we can conclude it's strictly monotonic. So this function must have an inverse function. Okay? If we take a look, all right, at the other function here, and we graph it, and we're taking a look, right? This is x cubed minus 1. Let me step back and graph real quick. So this right here, okay, if we're taking a look at increasing over its entire domain, if we restrict the domain, it can be monotonic on a specific chunk of the domain, okay? But if we take a look at the graph here, notice how there's a horizontal line test through points -1, 1, 0, 1, and 1, 1. So this function doesn't pass the horizontal line test, okay, so it does not have an inverse function. Okay, so when we're comparing these functions here, so the first one is x cubed plus x minus 1, strictly monotonic if we're looking for its graph, always increasing, decreasing. However, be careful, example B is x cubed minus x plus 1. Notice the two waveforms, okay? So based on horizontal line tests, we're able to deduce, all right, that there is no inverse function for x cubed minus x plus 1, okay? Not 1-to-1 on this case. So just some basic guidelines you can write down. Use Theorem 5.7. Solve for x as a function of y. Okay, we're going to do that. Interchange x and y, and that's going to give us the inverse function. And then you can define the domain of the inverse and the range of f and vice versa and verify them. Okay, so for us, biggest step, we want to be able to find an inverse function. Okay, so let's do that. Let's find the inverse given f of x equals 2x minus 3. All right? The easiest way to go about this, guys, is to switch x and y and resolve for y equals. Okay, so in this case, I'm going to take f of x, take it out of function notation for a few minutes, solve for y, okay, or switch x and y, then solve for y, and then put it back into function notation. Okay, so rewrite this equation as y. It becomes y equals 2x minus 3. Okay, now I'm going to switch x and y. So it becomes x minus 2y, or I'm sorry, x equals 2y minus 3. All right, so I literally swapped x and y, and now we're going to solve for y. All right, so we're going to add 3 to both sides, so x plus 3 equals 2y. Then divide both sides by 2. We call that y inverse, and then I'm going to put it back into function notation. Okay, so f of x inverse is equal to x plus 3 divided by 2. Okay, so we calculated the inverse function from the original function by writing it in terms of y, swapping x and y, and solving that equation for the new y, okay, which gives us the inverse function. Let's do another example of that. Find the inverse of f of x equals the cube root of x minus 1. Okay, so the first step, write it as y equals. Okay, so it's going to be y equals the cube root of x minus 1. Switch x and y. Okay, switch x and y, and now solve for y. So we have to solve this by, since it's a cube root, we're going to start by cubing both sides of the equation. Okay, so we're going to have x cubed equals everything on the right-hand side cubed. Well, the cube and the cube root cancel each other. Okay, so we're left with x cubed is equal to y minus 1. Okay, and then I add 1 to both sides, and that becomes y inverse. Okay, and then I'm going to take that y inverse and rewrite it in function notation. So f of x inverse is equal to x cubed plus 1. Okay, so those are inverses of one another. If you were to do f of g of x and g of f of x, both of these equations would equal x if we place them inside of one another and solve like we did in previous examples. Okay? All right, so let's do another one. We want to find the inverse function. We have f of x equals the square root of 2x minus 3. Okay, so we got a little bit more going on there. So we want to take a look. Does it reflect across the line y equals x? All right. So if we take a look at this, okay, swapping x and y, okay, and solving. All right, so the first thing, swapping x and y, and now we're solving. We're going to square both sides, okay, and resolve for y. Okay, so we get x squared plus 3 divided by 2 is the inverse function. Very simple to the last few that we just did. Okay, and replace the y with the f of x inverse, or f inverse of x, if I say it correctly. Okay, so swapping x and y, okay, or other method if you want, okay, solve the original function for x, and then swap x and y. Okay, that's what this one's showing you. We're solving the original function for x, squaring both sides, solving for x, swap x and y, okay, and then rewrite it as f of x, or f inverse of x. Okay, and we can clearly see the domain of the inverse function is the range of the original function. All right, if we were to graph these and take a look at everything. Okay, so existence, right, we talked a little bit about before, it has to be 1 to 1. The original function has to be 1 to 1, okay, in order for that inverse function to exist, or, right, it had to be monotonic on its specific domain. So we could look at the sine function, right? We should all know what the sine function was. I'm going to have the graph up in a second, okay? The sine function over the entire number line, negative infinity to positive infinity, okay, is not 1 to 1, right? Because y values are not unique. There's multiple ones. But if we restrict the domain on the sine function, say from negative pi over 2 to pi over 2, okay, it is strictly monotonic over chunks of sine. Okay, so if we put restrictions on the domain of sine, it can be monotonic, therefore being 1 to 1. So let's look at the graph of sine, right? Lots of, ununique y values over the entire number line. But if we restrict the domain from negative pi over 2 to pi over 2, okay, we are going to be able to say, it's strictly monotonic. So you can, base it down if a function is 1 to 1 over specific intervals, but not for its entire domain. Okay, it has to have a restricted domain, all right, for that to happen. All right, so last part, We want to be able to take the derivative of an inverse function. Okay, and this comes down to making sure that we understand the domain of one is the range of the other, and vice versa. The range of one is the domain of the other. When we do this, it'll help you doing the evaluation pieces. Okay, so write down Theorem 8. If f is continuous on its domain, the inverse is going to be continuous. If f is increasing on its domain, the inverse is going to be increasing on its domain. If f is decreasing on its domain, the inverse is going to be decreasing on its domain. If the original is differentiable, the inverse has to be differentiable as well. Okay? So, Theorem 5.9 says let f be a function that's differentiable on an interval I. If f has an inverse function g, then g is differentiable at any x for which f prime of g of x is not equal to 0, right? We can't have division by 0 in this case. All right, so we can write the derivative of the inverse function. And with this, I don't like the theorem as well to apply it, so I kind of rewrote it down below bit for you. You have to recognize in this equation here that g of x is the inverse function, okay? So we are finding the derivative of the inverse. So g prime of x is finding f inverse prime of x, okay? So I rewrote it kind of down below where I have f inverse prime of x is equal to 1 over f prime of f inverse. All right, because not everything is going to be written out nicely in terms of f of x and g of x. So you have to be able to understand how the inverse works. Okay, so if we write this down, so let f of x equal 1/4 x cubed plus 1 minus 1. We want to find what is the value of f inverse of x when x equals 3. Okay, so we got to be careful. We're looking for the y value of the inverse function, given the x value of the inverse function. Okay, so that x value of the inverse function is the y value of the original function. So you have to be careful for that. So we're going to say that 3 is equal to the original function and solve for what value of x gives us a 3 in the original function. Okay, now, sometimes it's hard to do, so use your calculator. Look in the table. When the y value is 3, what is the x value? Okay, so it's important. So, when we're looking for when the x value on the inverse is equal to 3, that's telling us that the y value on the original function is 3. So, we would say 3 equals 1/4 x cubed plus x minus 1. Okay, plug that into your calculator, and you will get that x is equal to 2. All right, so what does that mean? If we put x equals 2 into the original function up there, we will get back a 3. Okay, so f of 2 equals 3, meaning if we look at the inverse function now, f inverse of 3 equals 2. Okay, so what does that mean? The original point is 2, 3. The inverse function is going to be 3, 2. It's important because we're going to have to substitute that f inverse of 3. We know the output is 2 when we're taking the derivative on the next slide. Okay? So now when we do this, okay, we want to find f inverse prime of 3. So we're going to write 1 over f prime of f inverse of 3. We know that f inverse of 3 is equal to 2. We calculated that on the previous slide right down here at the bottom. Okay, so that's how we know that value is 2. So now we have to find f prime of 2 when we do this function. All right, so you got to take the original function, take the derivative of it. So you're going to get 3/4 x squared plus 1. Okay, so we're going to substitute 2 into 3/4 x squared plus 1. Okay? So very simple here when we do this. All right? Substituting in everything, all right, we get 1/4. And I'll do more examples of this in class, okay? But I think once we do 2 or 3 of these, we'll be good to go. So, all right, guys, this is the end of 5.3. Inverse functions. We'll go through more, like I said, in class. If you have any questions, please ask when you get to class. Else, guys, have a great day, and I will see you in class.